Welcome to the first Flood Risk Management Network webinars. This is the first of what we hope will be a monthly webinar series. We've got the speakers lined up for the first 2 or 3 of these, and I'm sure they'll be of interest to you. If you would like to nominate yourself as a speaker, or perhaps one of your colleagues, hopefully with his knowledge, please get in touch with myself. My email address is on the screen there, or Catherine, who sent you the invite for this webinar. Back to business. My name's Scott Arthur. I'm based at Rework University here in Edinburgh. The presentation I'm going to give today is called Debris and Flood Risk. This is really just a summary of work we've been doing over the past few years, looking at the role debris can play in flood risk and how that can be best managed. The presentation is basically a summary of a study report which we published late 2013. It provides an overview of work we've done in the field and also the laboratory. I'll give a broad overview of all of that work, and then towards the end of the presentation I'll focus more on the laboratory work we have done. The URL for the report is just below the graphic there, so you can download that free of charge and read it at your leisure. Don't rush to do that just now though, please stay for the talk. And I'll give you that URL again on my very last slide so that you don't forget. The telephone goes. Sorry about that, it's not my office. So culverts represent the pinch points in river systems, and trash screens are normally or are often installed to reduce the risk that they pose. However, these can be a risk in themselves if they're not maintained properly. And the material which reach the screens can be, natural material, woody debris from woodlands, or perhaps anthropogenic waste, fly tip waste, which often works its way into the river network. By and large, a broad rule of thumb is that if you install a trash screen, your maintenance will increase substantially in terms of the time you spend keeping that screen clear, but you would hope that the risk of flooding is reduced. So it's about, you're paying a little bit extra money to reduce that flood risk. Debris problems vary significantly from catchment to catchment. This is sort of inner city Glasgow, and you can see in the picture the range of debris there focuses on man-made. Here in Edinburgh, this is the screen closest to us, the catchment here. Most of the wood which reaches this screen is from a woodland, but the issue here is it's actually a managed woodland, and so there's opportunities there to perhaps manage the woodland in a different way to reduce the debris risk. And on that screen, this is the kind of debris that can build up over a single event. So it's quite different from the material I showed you for the Glasgow catchment, but it still represents a significant risk in terms of a blockage to the culvert, which is a little downstream from the screen. As you can see, most of the debris in this picture probably would have passed through the culvert without any problem at all. And the screen's job is really just to stop the larger pieces of debris. But the price you pay is it also stops a lot of smaller debris, and that's where a lot of the maintenance comes from. We've done a lot of work in Belfast trying to categorise the different debris types which reach trash screens. These range from small vegetation, as you can see, which dominates, domestic refuse, through to large household waste, which can perhaps categorised as fly tip waste. So you see here washing machines, lawnmowers, you're familiar with kind of things. Large non-domestic refuse, commercial, industrial waste, perhaps reaching the watercourse either deliberately or by accident. Larger pieces of wood debris and miscellaneous items, which are obviously exceptions, but still a concern if you're an operator as well. So a broad range of debris types there. So to help engineers manage the risk caused by debris, there's the existing guidance is available in the UK. We have the Environment Agency's Trash Screen and Security Screen Guide, and we also have the Syria Culvert Design and Operation Guide. At the heart of these is this graph here, which helps engineers estimate the amount of debris which may reach a screen over a given year. This is actually quite a useful tool, but what it doesn't do is allow engineers to estimate the debris which may reach a screen during a single event or perhaps over a shorter period of time. And it also, the catchment characteristics it picks up are actually quite limited. So the initial scope of the work was actually to try and give provide an analysis tool which would be more event-based. So I'm going to talk through some of the activities we're undertaking. This graphic here is to remind me that, particularly where the field work is concerned, uncertainty is a big issue because it's difficult to predict when debris is going to enter the water course, and its movement through the water course can take weeks, months or years, so the time taken to pick up an impact can be considerable. So there is a lot of uncertainty here, and you'll see that in some of the data. So the Belfast fieldwork, in Belfast they have over 500 screens. We focused on 140 of these where the data was most reliable. What we found is for some of them, the screen very rarely bopped. This is based on inspections every 2 weeks and during bad weather. And for other screens, well over half of the time they were visited, there was a blockage that had to be cleared from the screen. So you could see that the catchment characteristics and perhaps the screen characteristics itself have some role to play in the risk posed at individual screens. Sorry, this graphic's obscured. The animations don't seem to be working correctly on the software. So out of all the work we undertook in Belfast, we developed a model which reasonably reliably gave an indication of which catchments pose the greatest risk in terms of generating debris which would cause a problem at screens. And we also took into account screen characteristics. So using this approach, it's possible to rank screens in a catchment from the ones which perhaps would generate the highest maintenance activity or pose the greatest risk through to the other end of the spectrum. The key driver here is actually the catchment itself. What we found that, and this is broad generalisation, what we found is that the more rural the catchment, the fewer problems it posed. Coming into urban areas, higher levels of social deprivation were linked to greater problems. This is partly to do with the sort of culture of these areas, but also to do with factors such as there's a lack of space to store unwanted furniture and other materials. People perhaps don't have the same access to transport to take materials to a tip, and councils in general terms offer less of a service in terms of picking up debris or picking up unwanted materials from urban areas. So it can be quite hard for people to dispose of unwanted materials at zero cost. So it's quite a complicated picture. If you're interested in this area, there's quite a lot of work being done by I think the Jill Dando Foundation on fly tipping in general and the link to social deprivation and what the factors are which drive the fly tipping. and also methods you can use to reduce it. So building on that work in Belfast, last year we undertook some field work as part of the Blue-Green City project, looking at the movement of debris in rivers themselves. So the Belfast work looked at catchments producing debris and the impact on screens. This work was to look at how the debris moved through the river network. What we did here is we tagged pieces of debris which we collected from the river, so we knew they were representative, with small passive transponders. These are similar to the tags that supermarkets use to try and detect people that steal things from the shops. As the material moved down the river, the tags were individual, so we could track the movement to a certain extent of individual pieces of debris. This graphic here shows how the system works. We have to set up a loop antennae in the river to track the pieces of debris as they move through the river network. The technology itself is relatively well established, but the issue here is actually converting it to something that's deployable in the field. It's waterproof and can be used reliably. So really the experiment was proof of concept, make sure the technology works, and the next phase we'll look at actually using it in anger. Produced quite a lot of interesting results, which feature in a paper which we published towards the end of last year. Basically what we found is there's lots of factors which influence debris movement in the river, which do require more work to be fully quantified. The river cross-section, the geometry of the debris, the amount of vegetation, obstacles in the river. By and large, as you would expect, smaller pieces of debris are able to move further. But what we found is, in general terms, particularly when it wasn't raining, debris didn't really move very far at all, which is what's illustrated on the graph here. You can see the debris, which was deposited just a few hundred meters away from the antennae, never got as far as been detected. So laboratory work. Stress screens come in all sorts of different shapes and sizes, and I've yet to see one that actually looks attractive in any way. All of them have been designed with the same purpose, and that's to stop debris passing through them, which would cause the culvert to block. But I think the designers, to a certain extent, hope that the smaller material will be able to pass through the screen without causing a problem at all. So the aims of the laboratory work were to develop a physical model, and upon that produce an empirical model which we could use to better understand tri-screen performance. Flume-based study, we installed a 1/3 scale culvert in a flume, 1/3 scale of perhaps a 1 meter diameter culvert. The culvert itself had a head wall. With the screen we were able to vary burst spacing, the screen angle. We could vary the flow rate, the flow velocity, and importantly, as I'll touch on later, we were able to vary how far away the screen was positioned from the head wall. So we placed individual pieces of debris, and to really focus on the screen we used homogeneous debris, which were just straight pieces of wood, so we could just really focus on the performance of the screen. Placed these in the flow, and we waited to see whether or not they would become blocked on the screen or they would pass through. Quite a few students were quite busy with this. I think in total, quite a few undergraduate and postgraduate dissertations were completed on the back of this. In total, around 150 pieces of debris were passed down the flume, so it's a non-trivial amount of data. And as you would expect, after all that time and effort, as you would expect, the longer pieces of debris are more likely to block, which is what you would expect. But importantly, we were able to quantify that. We were able to look at under what circumstances long pieces of debris could get through the screen by approaching it end on. We looked at the the role of screen angle, and these angles are measured relative to the horizontal. And what you can see is that the flatter the screen, the more likely it was for material to block on it. So that's indicated by the 30-degree screen. We were unsure about why this was. We came up with all sorts of different theories, but none of these theories really allowed us to be convinced that we really understood what was happening. We looked at the bars themselves, the flow around the bars, the flow velocities, and upstream as well. And what we found was that the screen angle was a little bit of a distraction. What we thought that perhaps was important was not the angle of the screen, but perhaps how far away the screen was from the culvert head wall. Because obviously the more vertical the screen, if the screen is attached to the culvert head wall, the closer it is to the culvert entry point. So what we did was we installed a 60-degree screen in the flume, we maintained it at that angle, and we moved its position up and down the flume towards and away from the culvert head wall. And what we found is that the closer the screen was to the culvert head wall, the less likely it was for material to block on the screen itself. And the reason this is the case is to do with the fact that our culvert is smaller than the flume diameter, which is unusual for the culvert in a river to be smaller than the river width. So as the flow approaches the culvert, it begins to constrict. The flow velocity the flow path begins to constrict as it gets towards the culvert entry point, and the flow velocity begins to increase. So what we think is happening is that where the screen's not interrupting this by being placed at a shallow angle, material is able to align itself to the general flow path and perhaps get through the screen end on rather than blocking on the individual screen elements. So it's quite an interesting finding. It makes quite a lot of sense, but I guess the next challenge is to think about how that relates to screens in the field where material isn't nice and cylindrical and perhaps there's more interaction between material as it approaches the screen. But nonetheless, still quite interesting. So based on the back of all this data and a little bit more, we've developed empirical models which can be used to estimate what the performance of the screen is going to be in terms of being able to retain material which is reaching it. This is based on the first set of relationships are based on bar spacing, debris length, screen position, and screen angle. Now, in most cases, people who are responsible for managing screens, in most cases, people who are responsible for managing screens aren't allowed to dictate the length of debris which reaches the screen. So we did also build separate relationships which exclude the debris characteristics as a parameter. These relationships, as you can see, are a little bit messy, the kind of relationships students don't like remembering for exams, nor do we expect them to. So to get around this in the SERIA guide, what we've done is all the relationships are presented there. There's a simple nomograph, and we also have a spreadsheet available which allows you to enter your screen data in, and I'll give you some estimate of what the blockage rate will be. And because our culvert is a relatively small diameter, 1 meter diameter, the spreadsheet tool will also give you some warnings where we think perhaps you're trying to extrapolate the data to too large an asset. So in general, I think the work at Heriot-Watt is shown quite a lot of promise in the way that it's built on the existing guidance in quite a complementary way. Perhaps one of the issues is that it's still a little bit too academic, and it's not really that readily applicable by people in the field. So we're trying to address that as part of the Blue Green City project, where we will produce a tool which is a little bit more and focus where users can get access to this research much more readily. The Environment Agency has just embarked on a project to do something along similar lines. We're going to try and take existing research, more than I expect, just the work that's been undertaken at Heriot Watt, and try to provide tools which are usable by EA staff. I think GBA is leading that project. So what next? Again, animations aren't working here. What next? Really, we hope to extend the pit tag work because we think that's quite interesting, and we think that that's going to enable us to get more understanding of how debris moves through watercourses, particularly relative to the average flow velocity, so we get more of an understanding of how long it takes debris to move from the source to actually causing a problem at a screen or a culvert. Independent of that, we're just in the process of bidding for work to hopefully develop guidance for the design, operation and maintenance of automated screens. Some parts of Scotland, and I expect elsewhere in the UK, some screens are in quite remote locations, particularly those associated with transport infrastructure. So maintaining them can be quite an endeavour in terms of time and money. But the problems associated with failure, because it's linked to transport infrastructure, could be non-trivial. So we're hoping to undertake work to try and add some clarity to how automated screens, what kind of role they can play there. Okay, so that more or less sums up what I was going to speak about today. I'm only 1 minute over schedule, which isn't too bad. The link on the left is to the CDOG supplementary technical note, which I've spoken about. The link is case sensitive, but you can download that document for free. These slides will be available afterwards, including my narration. But if you want to get a copy of the actual slide file, if you just go for the link on the right, you should have access to that. Okay, that concludes the webinar. I hope it's been interesting, and even for people who have not really thought about this area of research or activity before, and I hope you'll tune in and spread the word about these webinars, and hopefully the next time we'll have an even bigger audience. Okay, thank you.